Hi, everyone, and thanks for joining me for this presentation. I'm Mira, and today we'll talk about neural city maps, a case for 3D urban environment representations based on radiance fields. Now, for those of you attending live, when you arrived this week, you probably experienced a first day similar to mine. You maybe spent some time walking through downtown Denver, and on your way passed through plazas like this one. Perhaps you even walked by this exact bear. When you finally arrived at this hotel, you entered through the revolving doors into the spacious hotel lobby. You checked in, got your room key, and after a little while, decided to head on up to your hotel room, which, if it's anything like mine, might look something like this. So you put your luggage down, settle in, a couple days go by, and finally, you're here with me this afternoon in a conference room like this one. Now, all of the videos I just showed you, as you can clearly see from this one, are not, in fact, camera videos. They are renders of 3D environment representations built using neural radiance fields, or NeRFs. NeRFs are a breakthrough from computer vision that exploded onto the scene in 2020. And they allow us to continuously represent 3D scenes using neural networks. Now, each of the NeRFs I've shown here were trained on very short video clips recorded by hand on our phones by myself and two colleagues. So we captured the videos, trained the NeRFs using Luma AI, and created these renders of these 3D environment models, all on the afternoon we arrived. So, given their extraordinary potential, I'd like to make the case to you today for using NeRF-based maps, or neural city maps, to represent urban environments. So, why might NeRFs be a promising basis for a 3D map representation? Well, first of all, NeRFs can be generated easily from camera images. Now, if you have additional information like LiDAR or DEMs, you can incorporate these to get even better NeRFs, but that's not at all necessary. A small number of simple camera images is all you need to construct a decent NeRF. NeRFs also have a constant memory footprint. So critically, for a fixed model architecture, regardless of how many images or what input image resolution you use to train the NeRF itself occupies a constant amount of memory. Now, compare that to the memory required to store the set of images that you use to train the NeRF, which grows roughly linearly with the number of images and grows even more dramatically with increasing image dimensions. So NeRFs provide an extremely memory-efficient representation. Now, NeRFs can also be trained on different data sources: cell phone camera images, drone images, vehicle camera images, virtual simulations, satellite imagery. All of these can be incorporated with NeRFs. These sources have different pros and cons. Some are readily available, while others involve more overhead to collect and identify the associated poses. Some sources are easier to update more frequently. And different sources are also better suited for different applications. Aerial imagery for drone localization versus ground level imagery for vehicle localization, for example. So a huge advantage of NeRF-based maps is that you can train NeRFs using whatever image sources best fit your available resources and the specific needs of your application. Now, NeRFs have demonstrated remarkable results in a number of vision tasks and are being studied for indoor pose estimation, but they have yet to be rigorously explored as an urban map representation. So here, we propose what we call neural city maps. These are 3D representations of urban environments that are based on neural radiance fields. And our goal is to explore their potential as cost-effective, memory-efficient, detailed maps that can be used for various applications like visual localization for autonomous vehicles. All right, so for the rest of this talk, we'll start with a bit more background on NERFs and how they work. We'll then look at a sample system for constructing and utilizing neural city maps. After that, we'll preview a potential application of neural city maps, which is urban visual localization. And finally, we'll finish up with a summary, and I'll quickly mention some related works being presented by my colleagues also this week. So let's get started with a brief background on neural radiance fields. Now, neural radiance fields, or NERFs, as I said before, are a tremendous recent breakthrough from the computer vision community. They are a method for solving the tasks of 3D reconstruction and novel view synthesis. Explicitly, what NERFs attempt to do is to synthesize novel views of 3D scenes given only sparse collections of 2D images with known poses. It's quite a challenging task, and their performance on this is really quite remarkable. In the original paper by Mildenhall from 2020, a NERF is defined as a learned continuous function that maps inputs, a 3D location and a 2D viewing angle, to two outputs, a volume density or opacity, and a view-dependent emitted radiance, or color. The NERF represents this function as a multi-layer perceptron, or MLP, with parameters theta. To render an image from a given pose, NERFs observe the following steps for each pixel in the image. First, a ray is cast from the camera into the scene that passes through the pixel. Points are sampled along the ray. For each point, the point's coordinates and viewing direction are input to the MLP, yielding a density and radiance as outputs. And finally, volume rendering techniques are applied to aggregate the densities and radiance values along the ray into a pixel color. And this is done for every pixel in the image. Now, to train the NERF MLP, we start with a set of training images, and using the NERF, we render images at the same poses as those training images, and then we compute the pixel squared error between them. So by minimizing this loss function, we can learn the parameters theta of the MLP. So with that in mind, let's look at a sample system for how we might create and use neural city maps for urban applications. We can start by dividing a city into overlapping regions in order to train a separate regional NERF for each region. We ensure that each location within the city is covered by at least one regional NERF. And to obtain consistent views at NERF boundaries, there are a number of strategies we can use, such as inverse distance weighting. For each regional NERF, we can source the initial training images from a combination of public databases and collected data. So for instance, Google Earth Studio can be used to generate some number of images for each region based on the available computation budget. And these images are then divided across the NERF regions and are used to train each regional NERF independently. Once we've done that, we store and maintain the regional NERFs for a city on a publicly accessible server. And based on the user's queried location, the server transmits the relevant regional NERF weights to the user. So more on that real-time querying process. To obtain a subset of regional NERFs relevant for their applications, like localization, users first send their approximate position to the server. The server then transmits the relevant NERF weights back to the user, and users can then perform onboard computations using the received regional NERFs and their available sensor measurements. And if the map subset becomes invalid during this process, so for example, from users updating their position estimate, users can simply send an updated query to the server and receive a new subset. Now, because the neural city map is composed of individual regional NERFs, these can be updated independently. So when new data from public image sources or perhaps collected by users becomes available, we match it by location to the corresponding regional NERFs. We fine-tune each regional NERF with its new data. And finally, we update the neural city map database with the new NERF weights. All right, So that gives us an idea of how neural city maps can be used within urban application workflows in general. But now let's look at a specific example application, visual localization in urban environments. So what would this look like? Well, we start with some collection of images and we use it to train our neural city map. Now we have an autonomous vehicle driving on the road with cameras collecting images in real time in the real world. So for a real image captured by one of the vehicle's stereo cameras, we can take a NERF render captured at approximately the same location, and then we would compare the two images, looking for matches that we can use to localize the ego vehicle. So let's actually take a look at this using some real world images. We use the Urban Nav Hong Kong Medium Urban 1 dataset, which, as many of you probably know, contains about 13 minutes of driving data collected along a 3.64 kilometer long trajectory through a typical urban canyon within Hong Kong, and includes sensor data from LiDARs, stereo cameras, IMU, and GNSS receivers. Now, using the dataset's ground truth GNSS data, we selected 3 locations along the driving trajectory and trained a NERF at each location using images sourced from Google Earth Studio. So not the driving footage, but virtually simulated aerial images. All right, so we'll look at 3 regional NERFs that together would belong to a neural city map of Hong Kong. And for each one, we show here a rendered video from the trained NERF. So the first location is the most urban canyon in nature. It's a narrow intersection tightly enclosed by 3 really tall buildings. The second location is somewhere in between. It has tall buildings on one side, but lower rise structures on the other. And the last location has the broadest area of road with no tall buildings directly adjacent, just some smaller ones and plenty of trees. So we train the NERFs by collecting images from Google Earth Studio captured in spiral trajectories at altitudes ranging from, as you can see, 45 to 118 meters high, essentially simulating drone paths. So again, we're not using ground level images or driving footage. The NERFs are trained on aerial imagery only. And the idea is to see how we can perform in this challenging cross-view setting. So to elaborate on the training a bit more, for each dataset, we collect about 2,700 images using Google Earth Studio. The images are originally at a 1080p resolution, which we then downsample by a factor of 4. And for each, we train on just a single NVIDIA GeForce GPU, and each of these took less than an hour to train. And for our NERF architecture, we use the NERFacto model from the open source Python-based library, NERF Studio. So once we have the NERFs trained for our 3 real-world locations, we want to see how well can we disambiguate between different locations. So as a reminder, at the top, we have a video of the NERF for this location, location 1, which was the worst urban canyon. And next to it, we have a real image captured by a vehicle camera at that location, taken from the Urban Nav dataset. And what we do for this real camera image is we produce a NERF render at a similar pose and a NERF render at a different pose in the scene. And to more easily spot matches or dissimilarities, we use segment anything to produce segmentation masks for all 3 images. So take a look. We can see that the NERF render at a similar pose produces some matches to the real world image that aren't really there in the NERF render taken from a different pose, like this building edge here, this turn at the upcoming intersection, or this building edge. Now, without being exact correspondences, they still appear sufficiently similar where there are no clear analogs in the NERF render from a different pose. But there are some challenging spots as well, like the front of the ego vehicle, which doesn't appear anywhere in the NERF, but is quite prominent in the vehicle camera image, or this ambiguous blob that resulted from unresolved dynamic objects in the NERF's training images. But overall, even in this challenging cross-view setting, despite the distribution shifts from a bright, cloudless day in the training images to a dim, cloudy day in the real camera image, we can see that the nerfs hold enough visual information to distinguish between different poses and therefore have strong potential for visual localization. So a similar exercise for location 2, which had the intermediate urban canyon character. Again, with a real camera image from UrbanNav, we put our nerf to the test in this cross-view setting. And let's look at the segmentation masks. Again, we see some really nice matches between the nerf at a similar but not exact pose that aren't there in the nerf render at a more distant pose, like this pair of buildings here, or these pairs of buildings right next door. We can even see some individual windows being captured quite nicely. And even this tiny building at the center here is a match. But again, it's not perfect. We again have the large ego vehicle in the real image and more blobs from dynamic objects in the nerf training. But again, overall, the nerf representation allows for disambiguation between similar and dissimilar poses. And lastly, location 3, we'll zip through this in the interest of time. We have our segmentation masks. Now this prominent building along the side matches beautifully between the nerf and the real camera image down to the individual windows. And this is rightly missing in a different view of the nerf. Even this pair of trees in the background is a match as well. But this time, lots of challenge spots. The ego vehicle again, the central guardrail is missing, so is this tall signpost. And instead we have more artifacts from dynamic objects in the road. But compared to the nerf render at a different pose, we would still have enough strong matches to guide us to a localization solution. And if you're interested in more quantitative results looking at different metrics for image consistency, please check out our paper. So the key takeaway from this is that even in a highly out of domain setting, a very different viewpoint, different weather and lighting conditions, different dynamic objects, nerfs can still produce matches with real world images to meaningfully disambiguate between different poses. So we believe that nerfs are a very promising basis for an urban environment representation that can perform well for tasks like visual localization. All right, so real quick, what have we covered today? We've demonstrated neural city maps as a promising map representation for urban environments. We've showcased nerfs created from a variety of image sources, from short videos taken by hand on a cell phone, to robot-mounted RGBD cameras, to synthetic drone footage produced by virtual simulations. We've proposed a simple system to create, query, and maintain neural city maps. And we previewed a specific application of neural city maps for nerf-based visual localization using real-world data. Now, if you're interested in other applications of nerf-based maps, my colleagues are presenting 2 concurrent works this week. In Wednesday's session D1, Adam Dye presented on neural radiance maps for extraterrestrial navigation and path planning. And on Friday morning in session D5, Daniel Nimati will be presenting a direct application of neural city maps for GNSS non-line of sight prediction. They're great works, so definitely go check them out. And finally, thanks to Ford Motor and Allstate for funding this work, and a huge thank you to my advisor and colleagues in Stanford Nav Lab for all their insightful discussions. And with that, I'm happy to take any questions. Thank you.